bird's eye view of the FMM, of the fast multiple algorithm. At the root level, sorry, at the leaf level, which is the finest level of the tree, that's where the sources, the particles, reside. One is going to do an operation which is called the particle to multiple, which means that we take all the particles and we construct a multiple expansion from those sources. That's the first operation we need, particle to multiple, and we use P to M to represent that. Then, once we've created all of those multiple expansions at the finest level of the tree, we want to have also multiple expansions at the higher levels, the bigger boxes. But we don't have to calculate them again from the particles, from the sources. We have a series representation that covers the same area of space, but only they are more refined. We just add the contributions of those more refined series representations by what's called the multiple to multiple translation. We translate the series from the center of the child box to the center of the parent box, and then add the contributions together. And then we have the multiple expansions at all levels higher in the tree. That is called the upward sweep. We're going up in the tree in this picture by doing this multiple to multiple translations. That is the other kernel, if you will, of the algorithm. Another operation that we need to perform. Then we need to do what is here indicated by the dashed red arrows, which is the transformation of the multiple expansions, which is the representation of the sources far away, to local expansions, which is the mathematical representation of all the far field locally in the evaluation area. And this is what we're going to use finally to evaluate the field. This is called the multiple to local translation. And it turns out that in the fast multiple method is the most expensive part of the algorithm. And so that's going to be the one that we're going to spend most time in. Then, once you have the multiple to local, so once we have the local expansions, product of that operation that we've just performed, the multiple to local transformation, we want to propagate that information back down in the tree. That's called the downward sweep. Basically, I have a local expansion, suppose that represents an area, a large area, and we want to be able to go down into smaller and smaller cells in the more refined levels of the tree and represent those local expansions. And finally, at the deepest level of the tree, at the level of the particles themselves, the bodies themselves, we want to do the interaction. And that's called the local to particle operation. The final interaction of the expansion at the center of an evaluation region with the particles themselves. And the sum of all of that is going to give the field at every single evaluation point. So you can see that in this in this sketch, you can imagine all of the operations that are involved in the algorithm. Now, there's a lot of mathematics in each one of these that we're skipping, but it gives you a broad brush idea of the whole algorithm. I want to first describe to you how we went about parallelizing the algorithm for just a cluster, say, of particles, not GPU, just an MPI parallelization of the fast multiple algorithm. Once you have this tree, once you imagine the whole algorithm as a tree, then you can come up with this strategy for parallelization, which is based on, again, imagining that you cut the tree at a certain level. This is here indicated by this thick line at level K, say. This sort of separates certain branches of the tree from each other. So as we perform the operations of upward sweep and downward sweep, if you imagine that each one of those branches of the tree that were separated is going to go to a different processor, then to perform the whole operation in parallel, this cut that we've performed in the tree was going to tell us where the communication has to happen. Okay? And so each branch that we've cut off, we call it a subtree. This subtree is going to be assigned to a processor in parallel, and we imagine first that we're going to have many more subtrees than processors available so that we can distribute them in a certain way, ideally to balance the load. And to do this, the next step, the strategy is the following. Take each one of those subtrees and estimate the work that is going to be required to be performed in that subtree, the computation, and you see each arrow that is being cut here by our thick red line indicates communication that needs to happen as we traverse the tree downwards and upwards. And this is certain communication that we can also estimate. Okay? Pen and paper, you can actually estimate that. So, for example, you could look at, boxes that are next to each other, and you say, well, I have to transfer the information from this box B to the box, the largest box here at level 2. At level 3, I'm going to have these smaller ones. At level 4, I'm going to have even these smaller ones. And I say, if the expansion that I'm using, the series expansion that I'm using to represent the bodies goes up to a truncation. Normally the series expansion would be infinite, right? But you truncate that series expansion and to a level, say, P. We use P. And so if the series expansion stops at P and I have to transfer so many of them, then that's the communication I have to perform. So you can estimate that, okay? And all of this was performed by a graduate student of mine who's just finishing now, and actually joined the Nagasaki Computing Center with Professor Hamada. So we're very happy he's starting his postdoc. Not so happy he's not finished his thesis, though. So we hope that that's going to be forthcoming. So now that you have this estimate of the work and communication, now you can construct a graph representation of the whole algorithm, where in this graph, in this picture I have over here, each node of this new graph, altogether new graph, each node here represents a subtree. So I can assign a weight to that node that represents the computation that is required in that subtree. Then I can assign a weight to the edges that go from one node to the other in this graph that represents the communication that needs to happen from one subtree to another subtree. And in this now graph representation of the algorithm in parallel, suppose that I have to now work in 3 processors, and I'm going to partition this graph in these 3 partitions here indicated in my picture, and we want to use a graph partitioning tool to obtain that with the minimum communication and the better load balance. That is, so you want to balance the weights W across all partitions and minimize the weights that you cut Cij, indicating communication, and that it can be done with a available open source partitioning tool. We use Parmenides in parallel, and all of this work is already accepted, soon to be published, and you can find the preprint on arXiv and the links to the publication on our website.
So, Lorena,
yes?
Just to clarify, is this done on a each data set basis before you run the code?
Yes. So in each set of sources, set of particles, before calculating the fast multiple evaluation of the field, you calculate the work, make a graph representation, and partition the graph, and then distribute. So your next question is going to be, well, so you have to do a lot of work before you actually do the work you need to do, which is calculate the field. So how much does it take to do that? Because there's an optimization involved here, right? So we did numerical experiments to see if this was a good idea or not. Let me see if I have some of those, but if they're not in my presentation here, they certainly are in the paper. And the preprint, as I said, is already available a few months ago. So let me just show you here. This is just a to show you that the result is the results from this partitioning, based on the optimization of a graph partition, is quite different than what you would obtain from sort of the straightforward partitioning, which is based on what's called a space filling curve. This is the standard sort of way that people distribute these sorts of algorithms. And on the top 2 colored plots here, you see each color represents a processor that that area was assigned to, and you can see that you have the quite uniform distribution for 32 cores in the left and 64 cores on the right. And at the bottom you have what results from using this approach in terms of where each subtree ends up in the processor set that you have in your distributed system. And the test problem is a highly non-uniform one, where all of your sources are distributed on this spiral curve, and the reason we did that is a very challenging problem. If you put a uniform set of particles on space, then distributing the load is not so hard. But if you have a very non-uniform distribution, then that's when it gets hard, because you're partitioning, right, your space in equal portions each time you subdivide. So some of those boxes are going to be empty. Some of the boxes, perhaps the boxes near the center of the spiral, are going to have a lot more sources, and so they require a lot more work. So that's where you want to be able to load balance. So that's the test, one of the tests that we report in the paper. And this is a result of the load balancing, what we call the load balancing metric, which is the ratio between the minimum execution time of one of the processors and the maximum execution time. Now, this is a fairly harsh measure. Normally, you find in the books, about parallel computing, that a good load balance metric is the average divided by the maximum, and we're using the minimum divided by the maximum. So even if one processor is kind of like not doing anything, it spoils your sort of. So it's a harsher metric than the average divided by the maximum. You see that? So what we see in some of my labels didn't come out well, but I remember that this one here with the solid squares is the result of using a a space filling curve, which is a standard distribution method that people use in the algorithm, and the other ones at the top are this load balancing strategy that I just described. And the different lines are different experiments. So one has 1 million particles, the other one has 4 million, and the other one has 10 million or something like that, if I remember correctly. And I've lost my numbers, but this is here 256 processors, or 256 there, and this is 128, and we do have a sort of degradation there of the matrix. This number, I don't know why I've lost my numbers. They're not there. But going back to, so let me tell you that top here is 1, so this is when they're equal, right? The bottom here is 0, and so somewhere here this probably is here around 0.6, and this goes all the way down, so this 0.6, 0.4, so this bottom here for the space filling curve is about, say, 0.25 or something like that. Of course, 1 is the best, so we're pretty close to 1 over here. These are the experiments with more particles, 4 million and 10 million, probably. This is 1 million, and probably this is the 1 million on a spiral, which is the hardest one.
So you were saying that you were using a harsher load balancing metric. Obviously, the harsher metric is going to be harsher on the ones that have poor load balancing. So, like, what does it look like if you do compare with something like the average case?
Well, that's a very good point. That's a very good point. It's harsher for everybody, right? But I don't have those results, and the reason is that when we ran this, we simply didn't get the average. I mean, it's a matter of hindsight. We should have done it. In hindsight, it would have been a good idea, but once the results were done, we didn't look at it.
But
I'm afraid.
To me, the shape of the top curve is more meaningful.
Yes.
The shape?
Definitely.
Yeah.
The fact that it's like slowly losing. Yeah. Of course, we do have a degradation here for 128, which we haven't explained, but this is the first published result with this code, and we continue working on it, and we think we can improve some things. Yes. You were asking a question? Mike. Yeah.
NCSA has another question.
So how are these particles distributed? Are these distributed at random so that you have varying densities, or are they sort of a continuous sort of thing? Or how did you do that? Because obviously a space filling curve isn't going to do quite so well if you have things that have regions that are very dense and regions that are not so dense.
Yes, exactly. So this set is for the spiral one. Let me see. I really am unhappy that I don't see the numbers and the labels. So I wonder if I could just pull the paper up. If you have patience with me, I might have it right here. Well, the proofs here. As you see, this is just coming out, but it was a painful. Oh no, this is wrong paper. This one. Okay. Those are the estimates of work. That's timings. That is so this is the type of results that you can find in the paper. Speed up. So this speed up, I didn't show it, but again, speed up we have up to 256 processors. That's the spiral sources on a space filling curve down here.